Okay, welcome to Unit 10 about acids and bases. This particular lesson is lesson 10.1, the properties of acids and bases. So acids have a couple different features. Aqueous solutions of acids have a sour taste. If you think about like lemon juice or tomatoes are acidic, lots of acidic foods that we eat. Acids change the color of acid-base indicators. They often change that colored paper to red. So if they started out as a blue paper, it would turn to be a red color if it's an acid. Some acids react with active metals and release hydrogen gas. You'll often see that if you place a metal into like a test tube, you place the metal inside of it. When it starts to have a lot of bubbles, that would indicate that you have a gas being formed, like hydrogen gas. Here we see that barium, a solid barium, if we were to put that into the test tube with sulfuric acid, you're going to see a lot of bubbles, which would be hydrogen gas, and then barium sulfate would be a solid precipitate that would sink to the bottom of that test tube. Acids react with bases to produce salts and water, and acids conduct electric currents.
Acidic foods often have a sour or tangy taste. The hot taste of many peppers is caused by a powerful plant acid called capsaicin. Acid-base indicators, such as pH paper, change color in the presence of acids. Acids react with bases to produce salts and water. When hydrochloric acid reacts with sodium hydroxide, it forms sodium chloride, or table salt, and water. Some acids react with metals to release hydrogen gas, as is the case in this reaction of hydrochloric acid and zinc. An electric current is being passed through this acidic solution, causing the filament in the light bulb to glow.
You should be comfortable naming acids, but let's review those a little bit. A binary acid is an acid that contains only two different elements. Hydrogen always has to be a part of an acid, and one or more electronegative elements, like our halogens or group 17. Some examples like HF, HCl, HBr, and HI. So how do we name those? The name of the binary acid begins with the prefix hydro, always. Next, the root of the name of the second element follows that prefix, and the name ends with the suffix "ic." So for example, if we wanted to name HF, we would put the hydro prefix. F is fluorine. So the root of the name would be the fluor, and then it would end in "ic," and we'd add the word acid. So hydrofluoric acid. Similarly, HCl would be called hydrochloric acid, hydrobromic acid, and hydroiodic acid. So the only time that you see that hydro prefix is if it's simply two elements together. In comparison, an oxyacid is an acid that is a compound of hydrogen, oxygen, and a third element, usually a nonmetal. So we oftentimes see this as hydrogen and a polyatomic. Like HNO3 or H2SO4. The names of our oxyacids follow a pattern. If the polyatomic ends in "ite," we change the ending to "us," and if it ends in "ate," we change the ending to "ic." So if you ate it and it was icky. For example, we have H and O2. We have hydrogen plus nitrite. The "ite" is going to change to "us." So we would have nitrous acid. In comparison to H2SO4, we still have hydrogen, but now it's combining with sulfate with an "ate" ending. The "ate" is going to change to "ic," and we have sulfuric acid. We do not have prefixes on these oxyacids, that's only on our binary acids. The names of their anions are based on the names of the acids. So you should feel comfortable naming oxyacids that end in "ite" or "ate", and their endings respectively change to "us" and "ic". Some common industrial acids include sulfuric acid. Sulfuric acid is the most commonly produced industrial chemical in the world. The formula for sulfuric acid is H2SO4. The 2 is coming from the 2+ charge of the sulfate. Sorry, that's a 2-. And then we also have a 1+ charge of the hydrogen. Next, nitric acid is coming when hydrogen combines with nitrate. They both have a 1 charge, so we don't have to cross anything. All our acids are going to be aqueous. Phosphoric acid is going to be H3PO4. The 3 is the charge of the phosphate, and a 1+ from the hydrogen, once again is aqueous. Both of these are used in fertilizers. Hydrochloric acid, we see the hydro prefix, which lets us know it's hydrogen plus the chlorine, a 1+ and a 1- charge. You're not going to cross anything, and that's an aqueous. We've worked with hydrochloric acid before. Concentrated solutions of hydrochloric acid are commonly referred to as muriatic acid. Muriatic acid is used for many things, sometimes used in your pool. Acetic acid is going to be hydrogen with acetate, so C2H3O2. You'd cross your charges, and this would be aqueous. Oftentimes you see acetic acid written as CH3COOH. A common name for acetic acid is vinegar. Pure acetic acid is a clear, colorless, and pungent smelling liquid known as glacial acetic acid. If you think about the scent of vinegar and what it looks like, it is definitely clear and colorless and has a pungent smell. In comparison to acids, on the other side of the pH scale, we have bases. Bases are aqueous solutions that taste bitter. Bases change the color of acid-base reactions to blue instead of red. Dilute aqueous solutions of bases feel slippery, like if you think about soap. Bases react with acids to produce salts and water. Bases also conduct electric current. So you see a lot of similarities between acids and bases, but also some differences. If we're talking about the pH scale, anything from 7 up to 14 would be considered a base. At 14, that's neutral, and as we increase pH, it's going to become more basic.
Basic foods often have a bitter taste. Bases frequently feel slippery, like this bar of soap. Acid-base indicators, such as pH paper, change color in the presence of bases. Bases react with acids to produce salts and water. An electric current is being passed through this basic solution, causing the filament in the light bulb to glow.
Next, we'll talk about a concept called Arrhenius acids and bases. An Arrhenius acid is a chemical compound that increases the concentration of hydrogen ions, which can be written as H+. Hydrogen has a positive charge. An Arrhenius base, in comparison, is a substance that increases the concentration of hydroxide ions, or OH-, in an aqueous solution. So an acid is always going to increase the protons, or the H+, and a base is always going to increase the hydroxide, or the OH-. Arrhenius acids are molecular compounds with ionizable hydrogen atoms. What that means is you could break off a hydrogen atom from that acid. Their water solutions are known as aqueous acids. All aqueous acids are electrolytes or can conduct electricity. If we look at this example of nitric acid and water, what's happening here is that the water is gaining one of these hydrogens. So the hydrogen is just flowing over to the water and creating hydronium. When that hydrogen breaks off the nitric acid, we're left with just the nitrate ion. So it has fully ionized, the hydrogen came off of the nitric acid, and we have a new compound called hydronium, and then we have nitrate. What hydronium is just like an extra hydrogen on your water. So it's called like a protonated water atom. Some strong acids you see on the left and weak acids on the right. A strong acid like hydroiodic acid in water is going to completely ionize. The hydrogen is breaking off of the iodine and going to the water. All of these are forming hydronium, and then their ion is all by itself. You notice that it's a forward reaction only, and we don't see any backward progression in comparison to our weak acids like H3PO4, which is phosphoric acid in water. Some of the hydrogen is going to break off, but not all of it. So we see that the H3PO4 loses just one hydrogen to create that hydronium, but then some of the hydrogen is still attached to the phosphate. We see a forward and backward progression, so this is not completely ionizing. So because they don't fully ionize or fully break apart, these are all weak acids in that right-hand column. The strength of acids is based upon how much they ionize. So a strong acid is one that ionizes completely in an aqueous solution, like we saw that hydroiodic acid. A strong acid is a strong electrolyte, which means that it could strongly conduct electricity. HClO4, which is chloric acid, HCl, hydrochloric acid, and HNO3, which is nitric acid. All examples of strong acids, they completely ionize or break apart when placed into water. Hydronium ions, a weak acid, releases very few hydrogen ions. Hydronium ions, anions, and dissolved acid molecules in aqueous solution. HCN is an example of a weak acid, which is cyanic acid. Organic acids that end in COOH, like acetic acid, are also weak acids. They're not going to completely ionize or have all of their hydrogen break off. Most bases are ionic compounds containing metal cations and the hydroxide ion. These bases are going to dissociate or break apart in water, like NaOH. NaOH is a strong base, so it'll completely dissociate into Na plus and OH minus. In comparison, ammonia, NH3, is a molecular compound and a weak base. Ammonia produces hydroxide ions when it reacts with water molecules, but it's going to be one of those forward and back reactions. Some of the hydrogen is going to go over and create that hydronium ion, but some of it is also going to stay with the nitrogen, so it does not completely dissociate, so it's a weak base. The strength of a base depends on the extent to which the base dissociates. Strong bases, just like strong acids, are strong electrolytes. You see a list here of strong bases on the left, like calcium hydroxide, which fully decomposes into calcium and hydroxide, in comparison to NH3 and H2O, which is going to be creating ammonium and hydroxide. Here you can see how hydronium and hydroxide play into whether it's acidic, neutral, or basic. If a compound has more hydronium versus hydroxide, it's going to be an acidic solution. The pH is going to be less than 7. If those things are in balance, we have a neutral solution with a pH of 7. And if hydroxide is in greater concentration versus hydronium, it's going to be a basic solution, and the pH is above 7.